Hello, everyone. I would like to thank you for joining the OPTICA Utopia chapter seminar. This will be a long-term regular seminar event, and we will soon get another splendid lecture just like the one Professor Armour will give us today. So please keep following us if you are interested. If you have still not been our member, you are more than welcome to join us. Interact with everyone, get research inspiration, and have fun. Join is easy and free. Simply log into your OPTICA account, click on the student chapter, and then select the country and Utopia chapter. We have organized lots of great events. Just like last week, we have free picking the buffet for everyone. So don't be shy to be one of us. Next, it's my honor to introduce our guest lecturer today, Professor Helmy. Joined the Department of Electrical and Computer Engineering of the University of Toronto with extensive experience in academic and industrial settings. He received both Master of Science and PhD degrees from the University of Glasgow. Between 2000 and 2004, he joined Agilent Technologies, where he was involved in developing different photonic devices, ranging from highly reliable submarine-class lasers to uncooled single-mode lasers to integrate photonic circuits. ARM's research interests include quantum nonlinear integrated photonic devices circuits and nano-photonic devices circuits using hybrid metallic architectures. The application domains where his group contributes include optic signal processing, communications, and sensing. Welcome, Amr. Now the mic is yours.
I hope you can see my slides.
Yes, we can.
What I would like to talk to you about today is the notion of hybridization of modes and plasmonic devices and how one can use that as a path forward to provide really high performance devices, particularly active devices, or in hybrid plasmonic structures, so much so that the performance of some of these typical devices, such as modulators, detectors, and even filters, passive filters, can outperform the best reported silicon devices of a similar function. Before I continue, I'd like to highlight the numerous contributions that the team has contributed. Much of this work has been contributed through the work of Yuan Su, Bohan Chang, and Charles Lin. Very early in the process, when Ma has done great contributions a few years back, existing team member that is expanding includes Nasser, Eric, and Francis. So this is the team that has done a lot of the work that I'm talking to you about today. The talk outline goes like so. I'd like to initially speak to you about a motivation of why would we try to improve upon and extend the pathway of photonics on silicon using metals, which are usually very inefficient, as opposed to silicon, which is usually very efficient. So there is a justification that comes from CMOS scaling laws that relate to that. I'd like to discuss a little bit some of the highlights about existing silicon solutions that address some of these CMOS scaling laws and the limitations in interconnections, and discuss the bounds that the silicon itself poses given its technologies. And I would like to jump into the platform that we have been defining and demonstrating, which involves metals and plasmonic type of guided modes to demonstrate devices. Devices that are chiefly targeted at data comms, but the capabilities go much beyond data comms. But this talk will focus on transmitters and receivers, TX-RX, using these plasmonic platforms. And then I will not only show the performance, but I'll also go ahead and compare it in systems where they are compared side by side with their silicon counterparts. Because this platform is very generic for any active devices, I will touch upon when I get time at the end about applications in conventional optical comms where these devices can still contribute significantly, and interconnections in optical computers where these devices can also provide critical functionality. So I'm sure this is not a surprise for many of us that the electronic industry is a $1 trillion industry. It's a $2 trillion industry, and it's increasing. The sort of cumulative growth rate that is annual is anything between 10% and 4%. Only in the pandemic did we see a drop because of issues related to supply chain. However, the growth itself right now is anticipated to continue to increase to the tune of 4 to 5% a cumulative growth rate. So there is an entire boom in key areas such as 5G, such as cloud computing, such as AI and autonomous driving that is motivating and driving this growth. So this growth is not just conventional consumer electronics that we all know, like smartphones. No, there are new applications that are driving this growth even farther up the scale. So with this enhancement in growth, enhancement in demand, that also has to come new innovations. These innovations has to do with the functionality within a given CMOS chiplet and beyond a chiplet. As I'm sure you're all aware, traditional Moore law scaling, which Moore law has intense sort of particularly focused on the transistor size and the packing density. And the assumption at that time is the computing speed and the power consumption will all scale the right way as you reduce the transistor size. However, as the transistors go to a certain size, when you reduce their size, that does not mean that the speed and the power consumption and everything else go the same way. They don't anymore because of physical limits. So how does one expand the functionality so one can meet the growth demands? Well, the industry, as evidenced in the last 5 years or so, started to focus on a different way to enhance the performance. Not only do we shrink the devices and pack higher density devices, but we recognize that every single chiplet, this one or this one or this one or this one, and a multi-chip module can only be made with a certain ultimate peak level of functionality, peak level of integration, and peak level of physical size. So you cannot make them more than 8 mil by 8 mil, because otherwise you will have to pay a very steep price in yield. So what the industry leaders have been doing, such as NVIDIA, Xilinx, AMD, and Intel, I mean, these became one round right now after merger, they end up having a multi-chip module system in a package where they have a mixed die function, so they can add a CPU, a GPU, a memory, an IO chip, all within the same package, but none of these are from the same node necessarily. They all do their own function and they all use the optimum node, optimum technology, optimal approach to meet that particular function. That's ideal because the yield itself would be much improved and the function itself of the system in a package would be much improved, much more so than just a single chiplet. However, it's well recognized that the SerDes, the interconnection between this chiplet and this chiplet and this chiplet and this chiplet, or here and here and here and here, is limited to about 100 gigabit per second. That is limited by physical laws related to the data rate, the power consumption, and the distance by which they can travel. So that poses a huge limitation to the performance of any system in a package because the interconnection within a chiplet ends up being vastly faster than the interconnected between the chiplets. And the system itself will be made out of the multiple chiplets. So you have to make it work. Why is this limitation? This limitation comes from various directions. The transmission loss. So if you're transmitting a signal as a function of distance at higher and higher frequencies, the loss in that signal becomes steeper and steeper, and hence you need higher power consumption. So this limits the total bandwidth itself. The IO bandwidth itself within the package is hundreds of terabits per second, and it's ramping up nicely. But off the package, the slope is much narrower. Why? Because of power consumption. So much so that if you look at the total power within a chiplet, you will find that a very, very large portion of it right now, if not most of it, is because of the power you need to take the data off of the chip and back onto the chip. That has nothing to do with photonics, by the way. This is chiefly sort of a microwave and electrical transmission line copper sort of argument related to CMOS. So if you would like CMOS to perform better, we're going to have to do something about this. The energy required to move bits in and out of the board and in and out of the package and on the chip itself even scales with bandwidth and reach. So the energy itself will go up if the reach is farther out or if the bandwidth increases. That is well known. Just the edge or the threshold at which the energy increases ends up being significantly higher if you go to uh, uh, basically different technologies, on chip versus in package versus on board. There are different techniques that are designed to give you the communication on chip, in package, and on board. And as you will notice, the communication for on chip and in package has been predominantly electrically right now with electrons. But on board, there has been electron work like PCIe, DDR, SerDes, but there's also photonic um, contributions like the recent optical PCIe companies that are giving us PCIe 3 and giving us PCIe even 5 in the future, delivering them with reasonable performance. However, there is very little work about in-package and on-chip optics that can help alleviate the bottlenecks that I just mentioned. This has a huge impact on what we see and what we are able to use in our lives. The logic density of the chips that are being shipped in the state of commerce and the state of the art keeps increasing as the years increase. There is very little evidence of saturation, although that might happen soon. Even the memory density itself, because of various reasons related to signaling rate, although the slope itself is changing, it's still showing some reasonable level of growth. However, look at the interconnect density. It's a disaster. The interconnect density in comparison to everything else is almost plateauing and in some cases even going backwards. Why? It has to do with power consumption. It has to do with bandwidth density. So the energy per bit as well as the bandwidth density. How many millimeters squared do you need to get how many gigabits across the board? So if you try to summarize all that in some sort of a very meaningful plot, this one has been developed by DARPA in their PIPES funding program, you will find that the efficiency or the figure of merit of communications is highest for electronic communication techniques like NVIDIA, high bandwidth memory, AIB, and the NVLinks. But the reach is extremely short. If you would like to enhance that reach, there are some techniques like PCIe. There is a new UCIe that is coming up here. UCIe is actually a new technique that precedes PCIe, but the optics ends up being around here. Longer distances, but significantly low figures of merit. So if we would like to help the bottleneck of electronic interconnections, we not only need to improve the electrical ones, but we also need to improve significantly the energy efficiency of the optical ones. And that's where we come in. What I would like to discuss with you is existing solutions. How is silicon, conventional silicon photonics, is faring with respect to this? So silicon photonics is very well suited for interconnection technology. It provides incredible amount of bandwidth density. If you look at the figure and animation on the right-hand side, you see that there are silicon waveguides that are usually ferry the light in and out of a silicon engine, and this silicon engine will have modulators, will have detectors, if you like, that ends up communicating the light between two different locations. This is fantastic because of the reduced signal attenuation that the optics provides and the ability to expand the bandwidth because of the wavelength division multiplexing and the fact that you can build on this really in a comparable fashion to silicon. In fact, I will show you an example which was built on a silicon chip alongside the electronics. Are there challenges? There are. The problem with us being able to replace electronic interconnection with optical interconnection is that the density. Here, there's not much you can do about the density when it comes to silicon photonics because they're all diffraction limited. Look at this nice little animation. You will look at the waveguide, and as you shrink that waveguide dimensions, you'll find that the modes within that waveguide are no longer bound. The modes are everywhere else in space. So that's not very good. And the fact that you have to thermally actuate these devices so you can get them working like a ring resonator modulator or even a Mach Zehnder means that the entire package is not compatible with silicon for CMOS when it comes to operation, because CMOS works from minus 40 to 120. Optics will then work over 3 degrees, and then you will need a lot of electronics stabilization, thermal stabilization, and power and space associated with all this to make them work. So optics is fantastic, but it does not really meet all the requirements that we have. Here is a notable example that is about 6-7 years ago, and the group ended up forming a company called IR Labs. Yeah, so this particular device example, if you will, is a device that is two reduced instruction processors that are communicating with a common memory via a bank of optical transceivers, all on the same CMOS. It was a big feat when it happened at the time, but it shows something very important. If you look at the density of millions of devices in the memory and millions of devices in the RISC processors, you will find they're matched only by a few hundred devices in the optics. Why? Because we cannot make optics any smaller, and because the dimensions of the devices themselves, by virtue of the fraction limit, are fairly larger. So that gives you a feel for why the bandwidth density of optics cannot compete with the electronics counterpart. So if you look at the driving circuits for the electronics, it's thousands of components. For the optics, sorry, if you look at the optical components themselves, they are the same area would only house perhaps two optical devices. That's the mismatch in devices. But over on top of that, to build these on the same chip as CMOS, you will find that the power consumption and the speed of the devices is really subpar, is lagging. However, to be frank, these numbers have been multiplied by approximately a factor of 10 by the same group in a company setting, IR Labs, beyond the work of that report. So what were they able to do when they improved the devices, et cetera, et cetera? That particular company have a test chip performance that has about 1 terabit per second per millimeter bandwidth density on the edge of the chip itself. So this edge and that communication give you a communication of about 1 terabit per second per millimeter. They have used approximately 5 picojoule per bit, not taking into account the laser and the cooling power. So the power is allegedly higher. But that overall provided a great confidence level in what optics can provide by alleviating the interconnection problem. Right, so what can we do different to alleviate some of these great achievements of photonics, if you will? Well, let's try to think about another alternative to use instead of silicon photonics. As I mentioned before, the silicon photonics counterpart looks like that, and it has a principle of guiding based on total internal reflection, as I'm sure many of you are aware. That means that this total internal reflection sets a limit, a lower limit to how small these devices can be before the light is no longer guided in the guide. However, let's look at another alternative, plasmonic waveguides, where notice that the bar, the scale bar here is approximately 1 order of magnitude smaller, yet the mode itself remains guided until dimensions far smaller than the dimensions of silicon. That means that you can scale plasmonic waveguides to become smaller while maintaining guiding, and that's just one advantage of plasmonics. You can make the devices smaller. But we all know that plasmonics actually are very lossy. Despite of their losses, there was lots of work, most notably in ETH and Zurich, which ended up making modulators out of these. The modulators worked on the regime of between 100 and 200 gigabit per second or gigahertz, which was a great feat. But the devices themselves were fairly large, on the sort of size of maybe 20 to 30 micron, which is similar to that of silicon photonics. And the devices themselves were relatively lossy because they use metals. So this regime of confinement of light versus the losses, where it can determine a lot about the performance, it was still lacking before our work. So what did we do? We ended up actually inventing a way to guide light in plasmonics, but in a multiple plasmonic waveguides at the same time, to the extent that it provides you with a mode confinement that is really superior than anything silicon photonics can provide, but with losses that are significantly smaller than what plasmonics offer. Let's be a bit more specific. Let's take a look at that waveguide. That waveguide, it turns out, will have modes in the upper part and modes in the lower part. And if you make the metal thin enough, you can couple these modes and have super modes. And these super modes have different properties. If you choose the right mode, and if you choose the dimensions right, you can interfere out the field from the metal region and change the Z component of the loss to become minimal. So what you can actually do is that you can reduce the losses at will by changing the properties by approximately 2 orders of magnitude. And we have recent results that can take it down by another factor of 100. So you can go down to 0.02 dB per micron. Typical losses of structures like that without that level of engineering usually give you 2 dB per micron. So there's a factor of 100, and we have recently learned how to have another factor of 10. But most notably, that's not really the achievement here. The achievement here is that you can achieve that while keeping your mode profile, and hence the ability to maintain the packing density to continue to be much, much smaller than what you can get with silicon. So that seems to be not completely solve the problem, but almost alleviate the problem of plasmonic losses by 2-3 orders of magnitude. If we can make devices that are also smaller than silicon photonics by 2 orders of magnitude, that means we have a factor of 10 to the 5 advantage in these devices over their silicon counterpart. What better demonstration can we use other than a passive device? A passive device made out of plasmonics has always been doomed by high loss. So if you look at cavities, for example, like the one showed here with a radius of 5 microns, compared to plasmonics, you will compared to silicon photonics, you'll find that usually their per cell factor or wavelength selectivity is usually down here. But if you look at silicon nitride, which is very low loss, you'll find that the wavelength selectivity is not so great, not because of the high loss, but because of the dimensions and the guiding. So they're right here. If you look at silicon, silicon is king. Other than, for example, up here, there is photonic bandgap devices. Silicon itself provides the highest wavelength selectivity of per cell factor because it has high index and low loss. Our work, for the first time, has metals in it, yet it is actually higher in its wavelength selectivity than silicon, but lower than photonic bandgap structures. If you look at these structures which we made, you will find when you tune them properly, they have a wavelength selectivity of 30 dB. 30 dB is something that silicon cannot reach, and it's something that provides a lot of advantages. Look at the free spectral range. The free spectral range is like on the order of perhaps 45 dB. This is remarkable. This makes these devices relatively or less wavelength selective. So that provides a record, which is still holding for the per cell factor. And remember, this is a very high per cell factor that utilizes metals. So in comparison to metals, this is a factor of 10 to the 5 better than metals, but in comparison to, or 10 to the 4, in comparison to silicon, it's a factor of 3 or 4 better. Let's look at another device that these hybrid plasmonics can do, a typical modulator. In these devices, we can design them fairly differently. We can design them in a fashion that can actually make them a triode, not just a single device, a triode. So these devices could be on the order of a few microns squared, 1 to 5 microns, and they can have their losses modulated depending on the bias of these 3 devices, or these 3 electrodes. So that's a very different way than modulating using electro-optic effect or using refraction. This utilizes, in this case, an epsilon near 0 effect. So when you have these, here's a typical device that has an area of 2 microns squared, and the device itself has got, look at this, the insertion loss of this device is a factor of 5 smaller than silicon. How can we have an insertion loss of 1 dB? Because the devices are very small and the losses have been reduced by a factor of 500. That's how you can make such a small device that has metals work like that. If you look at the extinction ratio, you will find the extinction ratio can be either 10 dBs or 3 dBs, depending on the voltage you use, over 100 degrees of temperature tunability, 100 degrees. So these devices, for all intents and purposes, are athermal. So that's starting to check lots of boxes that are very unusual because these are boxes that we cannot have achieved using silicon photonics. The devices themselves are fairly small. The RC time constant is fairly small. That's why their anticipated bandwidth is in the hundreds of gigs. We can only test them up to 26 gigs in our lab because that's what we have the speed for. But that's very promising, very low loss, athermal behavior as well as very high speed. These voltages are a little worrying, but they are not set in stone. They're dictated by the materials we have in our lab because this was fabricated in our clean room. Let's take a look at another device, detectors. Detectors are particularly important because they end up dictating the performance of the link power-wise. These detectors, because this material, by this device, by the way, I forgot to mention that none of these devices are crystalline. All the active materials are an amorphous materials. So not only that these devices have metals, they don't have even silicon crystal, they have amorphous crystal. So the detectors here could work based on photoemission in Schottky barriers, as shown in the diagram down there, the band diagram, where we don't have flat band without bias, but with bias, we could actually reduce the barrier and have photo emission, internal photo emission devices in the Schottky. So I will show you some results about 5 micron devices, but we have recently had devices that outperform that by 2 orders of magnitude. So if you look at these devices, you'll find the devices are approximately 9 micron squared, and you will find that their sensitivity is on the order of 55, minus 55 dBms. So that is a number that even crystalline materials cannot get. If you look at their responsivity, it's actually not very high. The responsivity is in the order of milliamps per amp, milliamps per watt. So why are they so sensitive? It's because of their noise. The devices are extremely small, very high quality junction, so the dark current is incredibly low. And when the dark current low, you will still have an extremely high sensitivity. That is a great advantage, but at the same time, we still need to take the responsivity up by a factor of at least 50 so we could cater to links. But if you can take them up by a factor of 50 with respect to these noise levels, then we will be getting sort of record, more so than these records, detector performance. The detectors are also fairly small and they have a very small RC time constant. So the devices work up to hundreds of gigs. We've only tested up to 26 given our test bed. So now that I've showed you the device component performance, I'd like to actually have some system level comparison to see how that implies. So we built a typical what that implies with respect to performance. So we built a very small sort of concept setup, transmitter, receiver, and the modulator and the detector were interchanged between silicon and plasmonic, while we use exactly the same electronics, grating couplers, etc., and we have a link that is one meter in fiber as a demo. If you look at the bit error rate of our devices in comparison to silicon, you will find that at a typical bit error rate of 10 to the minus 12, we do about a factor of 2.5 improvement on silicon photonics. But if you look at the devices with optimized electronics, so when I say optimized here, I say the drivers themselves, the TIA needs to have the right bandwidth, etc., so it can match the very high bandwidth devices. You will find that we can do a factor of 50 better than silicon for the same bit error rate. But there is something particularly important and different with respect to silicon. Silicon photonics needs a settling time because of the thermal sensitivity. We don't have any thermal issues. So the latency, which is a huge issue when it comes to computing, is a factor of 100 better in our case, if not more. So there is definitely a path using our technology to get to over 100 terabit per second per millimeter square, or 300-400 terabit per second per millimeter to meet the demand of interconnect in silicon. If you compare both systems, you'll find that the bandwidth density of the plasmonic-based devices are 100-fold larger than silicon. That's because of a few factors together, 100-fold. That's because the bandwidth is larger, the latency is lower, as well as the area is much lower as well. So that gives you a factor of 100 improvement. But the latency is much better too, as well as the energy per bit. So you're gaining on all grounds and not effectively paying for anything for that compromise. So going back to the famous plot with respect to the efficiency bandwidth density divided by energy per bit, you will find that the electronics are around here, the optics are around here. The recent silicon photonic improvements that have been sort of being demonstrated by IR Labs and others has been around here. The conventional plasmonics is just about at the barrier, the edge of that line because of the loss. But if you look at the hybrid plasmonic devices that we've been working on, they have figures of merit that is populating that entire quadrant, if you will. And that's exactly the quadrant that I spoke to you earlier on in the talk about how that quadrant needs to be filled. And right now, there isn't a very simple way to fill it. But the story is beyond that. You need to remember that all the devices that I've discussed with you are made out of amorphous materials. So here there's in principle a paradigm shift where instead of thinking about photonics and electronics in the future, there is an opportunity here to think about optoelectronic CMOS. How? Well, every single CMOS chip could be at the front end of line down here. And for every one of these, there could be an optical engine at the back end of line that can cater to it, or the other way around, or you can have the drivers down here catering for the optical circuit here. But the most important thing is that the devices that are carrying out the optoelectronic functions or the photonic functions do not need crystalline material. They don't need silicon real estate. They can be built at the back end of line because all the devices that I've showed you earlier are built with processes compatible with the back end of line. So that's a new sort of concept that optics does not need crystals and could still outperform silicon and can exist at the back end of line of CMOS. So that can provide a sort of a merger of both technologies that can enable an incredible number of things. I can tell you, for example, LiDAR, for example, just as one example, if you would like to put something like that in space, you will find that this involves as many A to Ds, D to As that you need, as many antennas and grating couplers as you need up here for optics, so you can you can add both. If you're familiar with some of the sort of analog photonic, for example, company that is building incredible LiDARs, you will find that the number of A to D, the DAC chiplets that they have to co-integrate with the optical engine that they have is profound. If one can merge these together, you will find that it will be extremely advantageous from a performance standpoint. From a standpoint of other technologies, this is a platform technology. It's not a one-trick pony. It can do other things. Let's take a look, for example, the typical modulators. The typical modulators that I spoke to you about could be made out of 3, if not more, contacts. Why? Because the vertical structure is fairly versatile and the guiding itself is very compact. Why would that be useful? Because if you can have a triode like this, one would be able to tune the relative voltages of VA, VB, VC with respect to one another. And for given biases that you have up at a lookup table, you can have the device act like a on-off keying, 0 and 1. You can have the device act like a phase modulator, pi phase minus pi phase, if you see what I mean, or 0 phase and pi phase. So in that case, you can have phase modulation as with no change in the amplitude and amplitude modulation with minimal change in phase. That sounds like the ideal textbook example of a modulator. But then you could use these biases in a fashion by which you can actually have coherent modulation too. Like you can change currently the phase and the amplitude to give you QEM, DPSK, and everything in only one device. Why is that important? Because that is, if anybody in the audience is familiar with coherent communications, you will find that this is a holy grail on the scalability of the symbol rate. By going up to higher symbols involve a significantly higher number of Mach-Zehnder modulators. But here, through the bias, one is able to change the amplitude with no phase change and to change the phase with no amplitude change. This is the key to be able to have a good modulator like a QM or a DPSK modulator. But in this case, we are achieving it in one device, albeit a little bit longer than the previous devices I'll show you. So this device could be on the order of maybe 30, 40 micron to do all that rather than 10 micron. And still, about a factor of 100 less than the number of devices and the area you need to build a QAM using silicon modulators. So that's an advantage that can bear fruit, particularly in optical communications. So if you look at the figures of merit of these modulators for QEM and DPSK, you will find it's at least a factor of 5 or so better than the best figures of merits of the modulators themselves by virtue of energy consumption as well as the extinction ratio on losses. So that makes them even a more compelling modulator, despite of being very small, when compared to silicon modulators for optical comms, not just data comms in CMOS, just optical comms generally. If you look at the other side of the transceiver, look at the detector. When you compare the detectors that we have reported recently with many others, particularly made out of crystalline silicon, all of these, you will find that our sensitivity is higher by at least 25 decibels. So a factor of 500, if you like, fold. So that, or 200 rather, fold. So that's a fairly large step change when it comes to detectors. Why is that important? That's extremely important when it comes to power budget. So the optical comms and the data comms have very stringent power budgets. And if you would like to reduce that power budget and by having more sensitive detectors, then this could be, these detectors could be used. So as you can see in the optical comms domain, these devices could be just as powerful as for data comms. When it comes to their utilization in optical interconnects, it's also a very interesting subject. Optical compute fabrics right now are doing a fantastic job in connecting a few qubits together, 4, 6, 16 together. Obviously, every linkages between these involves a 2 to the n increase, if you like, 2 to the n increase in the computing power. So if you have 4 qubits connected, that provides you with a 16-fold increase. So as you can see, there is an exponential increase in the power of compute if one can utilize larger and larger compute fabrics. But these quantum compute fabrics and qubits are not very easy to scale. They are large. They have lots of other control circuitry that are needed on the same chip. Wouldn't it be incredible if one is able to actually enhance all this by getting these compute units interconnected optically? So then they look as though they're one quantum computer and they get the exponential scaling power, but at the same time, they are in reality a few smaller modules of quantum computer that are interconnected quantum mechanically. And the best way to interconnect things generally is optics. So the idea here is for us to have a quantum compute fabric and another quantum compute fabric and another one connected to one another using flying photons, as we call them, at 1550. But these photons end up having the quantum state of every module that it started from to link them to the rest of the fabrics. Why is that important? Because that means that these 4 fabrics could act as though one quantum computer. That interconnection is difficult to achieve. And one of the reasons why we believe we can achieve it is because of the confinement that we have in our structures, the Q factor that we can have, which can connect the superconducting qubit, for example, with the optical qubit and connect them that way. I think I'm out of time, but some of the cavity performance metrics that we have shown in our plasmonics point to the ability for us to be able to have, given the Q of 10 to the 4, which can be enhanced even farther, can allow us to relatively efficiently connect our optical qubits with electronic ones as well. So that's another application where this platform can also contribute significantly. I think I'm out of time. I promised to speak for 40 minutes and we're coming up to 40 right now. I wanted to thank you for the opportunity and to open the floor for questions. Much appreciated.
Splendid lecture. Thank you, Amr. And I would like to ask if any audience have questions or comments, just please be free to unmute yourself.
I had a question I wanted to ask.
Please.
So in the slide where you first introduced the coupled hybrid plasmonic waveguides, you talked about super modes and how those were like kind of the trick, I think, to alleviating the loss that you have in the plasmonic waveguide otherwise. Could you just explain what that means a little bit more? Like what's a super loss, a super mode compared to a normal mode that, like, I guess I would imagine in a waveguide?
Sure. So if we look at that waveguide, you will find that this particular stack could be divided into two. There's a stack up here and there's a stack down here. This particular example has a stack of a dielectric and a metal. So the modes around the dielectric and the metal they look like this red line, and they are SPPs, surface plasma and polariton. If you look at the lower stack, keeping the metal as a common denominator between both, you will find that you have a metal, low index dielectric, and high index dielectric. That can support what we call a hybrid plasmonic mode, where most of the intensity is in the blue low index dielectric right here. This is a waveguide on its own right, and this is a waveguide on its own right. All what we've done is we've actually merged them using a common metal layer, and when you merge them, it's just basically like two hydrogen atoms. If you merge them, this mode and that mode will couple. If they couple, these modes will not cross. Like if in the dispersion diagram, they will actually do this, and sort of basically they will transform into two modes, but not this or that, two hybrid modes, a combination of these. One of them is symmetric and one of them is anti-symmetric. And the symmetric and anti-symmetric modes, one of them is the low loss waveguide and the other one is a much higher loss waveguide. And the detailed example of that is here. So if you look at the mode in here, you will find that this is a mode that is made out of this SPP along with this hybrid mode, hybrid plasmonic mode. If you couple them together by making the metal sufficiently thin, you make a super mode. And if you choose it right, you can minimize the metal inside you can minimize the field inside the metal. So the blue around here is the least, right? The blue here is larger and here is larger. That's the area that will have the lowest loss. It's in Science online version in 2019. Does that answer the question?
Yes, thank you. That's fascinating. Thanks.
Much appreciated. Yes, no problem, bro.
Well, Amr, I have a question.
Please.
Why you choose the metal, the material for aluminum? How about another metal like gold or silver?
If we choose gold or silver, we would get a factor of 10 improvement in everything I mentioned. So every single parameter I mentioned to you will improve, like the insertion losses, the propagation losses, a lot of other things. But we intentionally used amorphous materials that increases the loss a bit, and intentionally used aluminum that increases the losses a lot. So then this stack and all the devices that I showed you are compatible and completely realizable using amorphous materials at the back end of the line of CMOS with no crystalline materials and no layers that are extrinsic to CMOS. That was intentional to show that all this could be built in a fabrication facility at TSMC or Global Foundries without any need for major modifications.
I got it. Thank you. Thank you. What about the metals of the same family?
Lots of metals of the same family will show similar performance. But if you go to exotic metals, there might be advantages there to be had. And there's lots of advantages when it comes to 2D materials. But the key, if you want to make this a CMOS engineering achievement, you wanted to use things that the CMOS folk are very comfortable having in the reactors on the line. And these are the materials that we use. Anything else will be an interesting engineering/physics experiment, but the CMOS guys will not want to touch it from a processing and contamination standpoint. So we did that intentionally. And as we get funding to this and as we work on this, we will do more demonstrations using these other fancier materials and other less CMOS compatible materials, but ones that are more amenable to higher performance.
Many thanks. I got it.
My pleasure. Pleasure.
Amaudi, may I ask a question?
Please.
Yeah, that's very splendid talk, and thank you very much. And thank you very much showing my face all the time. And
My pleasure.
So my question is related to the first question. This slide, you said that the supermodes can reduce the field in the metal region, right?
The supermodes can be engineered, and it depends on what you want to do with that engineering. Like in another world, in the quantum world that I work on, we sometimes engineer the modes to have different dispersion, for example. We don't quite care about dispersion here. So the engineering is what you would like it to be. Engineering these modes could achieve many feats. One of which, what I just showed, is that you can actually
yes, and I understand that the field in the near the metal region add the loss of the waveguide, right?
Correct.
But my question is that does the plasmonic effect still exist even when you reduce the field near the metal regions?
Absolutely. If you look at the modes field here, it's only about 20% different. The plasmonic mode still exists.
Okay, so
you're just keeping it at the surface of the metal rather than at the, like if you look at the, let me just try to remove this. I'm not sure. Oh God, sorry. I do apologize. If you look at the field here, it still exists, but it exists on the edges of the metal, and it does not propagate inside the metal itself like here and here. So the plasmonic mode absolutely exists.
Then what determines the minimum the loss in this case?
The minimum loss?
Yeah.
In this case, it's approximately 100-fold smaller than the loss of the modes that it's made from.
Is that determined by the metal?
Yes, yes. So if you look at the loss of one of the modes, it's here. The loss of the other mode, it's here. The loss of the composite system, it's down here.
Okay, thank you very much. Then another question is that another way of reducing the size of the waveguide is to use a slot waveguide, isn't it? And if you compare this waveguide with a slot waveguide, what would it be?
The slot waveguide will give you about 37% to 45% power inside of the slot. The rest is going to be in the high index material on the sides, here and here. So that gives you very low efficiency if you'd like to use it for detection or modulation, because only a very small fraction is in the slot. By definition, like the slot is useful, but it's useful to within a factor of 3 or so, not a factor of 100. Besides, also the slot waveguide papers and results that are out in the literature, they conveniently don't mention something very important. When you have a slot waveguide, the mode is extremely unstable because you have a high index material, and the mode is right here. So this is an anti-guided mode. Eventually, for a long enough structure, it might eventually couple into this high index material again, unless you have lots of, like for a long device, if you like, it's not very stable to have the mode right here with an index smaller than the region light next to it and the region light next to it. And also launching light in that mode is not trivial. It's very resonant, because if you don't launch it with the right resonance, it will couple it into the high index on the sides. So it works, but it has some limitations.
Okay. Thank you very much.
My pleasure. Well, thank you everybody for listening and for coming to your laptops, I guess. Yeah.
Yes, thank Amber. And we are super glad to have you visit our lab. I hope you enjoyed this in Tokyo.
Thank you. Yes, I had a fantastic time in Tokyo, actually. Thank you for the invite and for having me. I really loved my time. Thank you, everybody, so very much.
So it seems there's no any questions or comments. So I would like to end this meeting. And I would like to thank you all again for joining our OPTICA seminar today. Have a nice day, you guys.
Thank you. Thank you.